On May 21st, 2024, a violent tornado would tear through the town of Greenfield, Iowa. This highly documented tornado would yield the fastest tornadic wind speeds ever observed with radar, but despite this, would only earn an EF4 rating based on the damage alone. My name is Ethan Moriarty. I'm a mechanical engineer by training, and this is a forensics engineering-based damage analysis of the Greenfield, Iowa EF4 Tornado. Before diving into the analysis of the damage, let us first go behind some of the stats of this tornado. This tornado was on the ground for 43 miles, peaking out at a max width of 1,600 yards, or nearly a mile wide. It was on the ground for a total of 48 minutes. In terms of the human impacts, there were 5 fatalities and 35 reported injuries. Though it is important to note, while injuries are not fatalities, these can still be life-altering injuries in the form of spinal injuries, head trauma, or even amputations, so it is important to treat this number with a great deal of respect. The estimated material impact from this tornado comes in around $32 million of damage. The National Weather Service would rate this tornado an EF4 with peak estimated winds of 190 miles per hour, though it is important to note that the Doppler on Wheels program observed tornadic wind speeds of 318 miles per hour with mobile radar. But as we know, given the limitations of the current EF scale, this was not used in the final rating of this tornado. I'm going to defer the meteorology of this video to Trey Greenwood of Convective Chronicles. He created an in-depth forecast discussion video of this event the morning of, and frankly, it's in much more detail than I could dive into here. That'll be linked below for you to check out after this presentation. However, it is important to note that the Storm Prediction Center did a great job forecasting this event. They implemented a moderate risk for severe weather, or a level 4 out of 5 for the region, driven by a 15% hatched probability for significant tornadoes. Ahead of the Greenfield, Iowa tornado, there were tornado watches in place, and the affected communities got advanced lead warning time tornado warnings. To start off this damage analysis, we're going to get an overarching view of the tornado's path in order to get a quick summary of the tornado's life. The tornado touched down southwest of Nottoway, Iowa, while the Carbon, Iowa EF3 was occluding. The first several miles of this tornado produced low-end damage, with the first EF2 damage indicator occurring 14 miles into the tornado's life. East of Carl, Iowa, the tornado would traverse through a wind farm, destroying multiple wind turbines, as well as several farmsteads along the way. The first EF4 damage instance would be 3 miles north of the town of Williamson, Iowa, in the form of a family residence. Towards the end of the tornado's life, it would jog from its north-northeast original course into a northeasterly course, impacting the town of Greenfield. It would avoid the downtown part of town to the south, but there was still multiple residencies in the path as well as small businesses, causing the bulk of the damage associated with this storm. The tornado would ultimately rope out just 3 miles past the town line of Greenfield. I think it is important to note that the majority of this tornado's damage occurred at the end of the tornado's life while it was beginning to occlude. This is clear because the tornado had rapidly shrunk in width and deviated from the parent storm's motion. With that decrease in width, we have a conservation of angular momentum, where because of the shrinking diameter, the wind speeds ultimately had to spin faster in order to conserve that angular momentum. The first subject of this damage analysis is going to be the wind turbines that were ultimately impacted by this tornado, as I think they are a fascinating case to look at in terms of some interesting failure modes. This image here is one of the turbines that had ultimately been taken down by the tornado. Most of them failed in this fashion, and we're going to dive into exactly what type of failure this is. Essentially, what ultimately happened is, as the tornado was traversing through this wind turbine farm, they were pushing over these wind turbines. But what ultimately failed in order to push these things over? As we can see at the base of the wind turbine here, it wasn't an anchoring failure. Otherwise, the anchor bolts that are very beefy in the case of wind turbines, just because of the fact of the daily loads that these things need to take, those remained intact, But if we look further up, we notice a couple of breaking points within the tower of the wind turbine, and these are a result of a buckling failure. A buckling failure is when a structural member fails laterally due to a compressive load, and we're going to dive into that more in depth and get the numbers out of it that resulted in these buckling failures. I was able to do a little bit of digging and find the manufacturer and model of these wind turbines and get their data sheets and ultimately get a lot of the geometries needed in order to perform this analysis. So some assumptions that were done in this analysis: the failure was within the tower section, not the tower fasteners. So what I mean by that is this tower is made up of a bunch of different segments, and fastening those segments together are a bunch of fasteners. However, based on the imagery and the videos that we saw of the tornado impacting these, we could tell that they weren't a fastener failure because the sections would be physically coming apart in that case. The ultimate failure was the buckling failure within the section itself based on the video evidence. So in this case, we know that the fasteners are much stronger than that of the tower section itself. We're doing this analysis as a uniform wind load. Granted, there's probably going to be a little bit of a gradient given how the tornado wind speeds are distributed, but for the purpose of this analysis, it is easiest to do a uniform wind load across the entire body of the wind turbine. The turbine would be in a shutdown state given that wind speeds were in excess of its operating parameters, so the blades would be feathered to 45 degrees, which is important to get into when it comes to the coefficient of drag influenced by the winds on the blades. We're treating this where the turbine is directly facing into the wind, which was evident in some of the videos of these turbine failures. And we're also going to assume that fatigue stresses were not already a factor into the failure. These are newer turbines based on satellite imagery, some of them only being a couple years old. So fatigue stresses are something that occur across the life of the turbine. And because these are such newer turbines, very early into their lifespan, they haven't had the constant wind loading of day-to-day use that would ultimately contribute to fatigue stresses, weakening them in the long run. So fatigue stresses are not going to be considered in this analysis. Now, here are the geometries that we are going to need for this analysis. So we're going to have a lot of the different geometries of the tower itself, as well as some of the distances. So for example, the height of the hub, the length of the blades, width of the blades. All of these parameters are important in order to get the geometries correct in order to put them into our drag equations as well as our sum of moments equations. I was able to get the weight of the turbine from the data sheet as well as some of the material information of the tower support. Since the failure was within the tower itself, it was important to get the material properties of that tower in order to analyze its failure. Additionally, we got coefficients of drag for the different aspects of this wind turbine. So you have the hub drag coefficient, the drag of the tower itself, and then the drag coefficient of the blades. So how these turbines work is they have feathered blades. So depending on what is needed for power output, they feather the blades based on wind speed in order to get the max power output out of those turbines. And eventually when the wind speeds become too great for the turbine itself, basically you have to shut down the turbine to keep the turbine from basically exploding. So what they do is the blades feather to a point where they can no longer produce lift. And when they do that, they produce a lot more drag. So even though that the wind speeds are a lot higher beyond the operating parameters of the turbine itself, there's still a lot of drag being pushed on those turbine blades. So that's why the coefficient of drag is so high on each of those turbine blades. Here are all of our forces on the turbine. So we have wind loads on each of the blades, as well as the tower and the hub. And then of course the weight weighing down on it and our reactionary forces at the base. So ultimately what we can do here is create a resultant vector because we're gonna average out these three blade heights and just say that they're acting into the hub. So we'll have the three wind forces combined going into that 95 meter height in terms of our input into our moment equation. So here we are kind of looking at a cross section of the tower. This is the cross sectional radius of the tower where it failed. This is a tapered tower, it being around 2 meters at the top and 4 meters at the base. So we took the cross-sectional radius at the point of failure. Here is our moment equation. So basically, we sum all of the moments about the base of this tower. So we have our critical buckling force, which is going to be this compressive load here. And then we also have all of our wind forces that are combating into this critical buckling force. So that's where this big M comes into play. That's the combination of all of these guys here. So with our governing moment equation, we can start solving for the force of drag equations on each of the elements. So this is for the hub of the tower. So we know the density of the air, we know the coefficient of drag, and we know the platform area, which is basically the exposed area that the wind sees that is acting upon that surface. And then the only thing we don't know is the speed of the wind. Therefore, we can do that for our other bodies as well. So this is our blade drag equation, and then this is our tower drag equation, all of which now are in terms of this velocity term that we can solve for after. We plug in all of these values to our moment equation. These are the moment arms, so how far the force is acting from the base. So as we remember, the compressive force from the neutral axis is only at that radius of 1.75 meters, whereas if we're looking at the wind forces that are pushing on the tower, they are much greater. So, 95 meters, and then half of 95 meters in the case of the tower, since it's acting right in the middle of the object. But nonetheless, we have all of these terms filled out here, but we need to solve for that buckling force, right? So what we can do is use our Euler's buckling equation, which basically what it does is it accounts for how the shape of the cross-section is and how good is it at reducing the risk of a buckling failure. That's what this I term is. Then we have E, which is our modulus of elasticity. So basically the material property and how good it is at resisting those compressive loads. Then we have a K factor here, which is basically the buckling end condition. So depending on how each end of our rod is constrained, you're going to have a different K factor. In the case of a turbine, you have an anchored end on one side, and then the other end is free to move. And because in that case, that effectively doubles the effective length of the buckling condition. If it's pinned on either end, you only have the length of the column to work with, whereas if you have a little bit of flexibility at the top, you effectively double that length working in your favor. So we plug in all of our values here since we know all of that. Granted, the data sheets had everything in metric, so the calculations here are going to be in metric, but I'll convert it in the end to miles per hour. So ultimately, our critical buckling force here, the criteria that we need to hit in order to result in a buckling failure of this tower, is 4,670 kilonewtons. That is a lot of force, but nonetheless, what we do now is plug that into our greater moment equation. So here is our critical buckling force, the distance from the central axis of that tower, and then our condensed value, since we could add up all those terms since they were all in terms of V. So this is the cumulative wind load basically from that tower. Then ultimately, because V is the last outstanding variable, we can condense it. We check our units to make sure that it is in meters per second at the end result, and we get an ending value of 51.9 meters per second, or 116 miles per hour. This is very interesting because the ultimate final rating on these wind turbines was EF2 117 miles per hour. So it's kind of funny to see how scarily accurate we can get with a couple of hand calculations at the end of the day. Granted, we can get into much more depth when it comes to how these towers fail if we use something like an FEA software or a finite element analysis software, where we basically plug this geometry into a giant supercomputer and make a bunch of little elements and see how all the stresses behave at different points in the structure. But That requires some very heavy computational power that I don't unfortunately have access to. With that said, let's kind of take a look at the sequence of failure events. So ultimately, the first failure is going to be a buckling failure at the top of the turbine. So you basically get that compressive buckling failure on one side, and then as this thing starts swinging over, we get a secondary buckling failure closer to the base. So this bigger cross section, as this thing starts swinging over, there's going to be much more of a compressive load building up now as the moment arm keeps swinging further and further, and you have more leverage pushing down at the base of that column, and it results in that secondary buckling failure. And then finally here we have a thread tear out at the tower joint from when the turbine itself smashes into the ground. That big impact force is just going to shear all the threads out of the bolts in the joint of the two sections of the tower there. So very interesting combined failure here. And if you haven't seen the video from Reed Timmer of these towers following over, you can actually see the sequence of events where they fail in the middle first, they buckle at the bottom, and then finally the turbine smashes into the ground and causes that final column section separation. This next damage analysis subject was submitted to me on Twitter. I had asked people if there were specific things that they wanted me to look at when it comes to the Greenfield, Iowa tornado, and this is one of the ones that came up. This was from a garage on the southern edge of the core of the tornado as it was coming through Greenfield. It is a 2-post car lift garage, and what happened here is basically a concrete tear out from the concrete base of where this 2-post car lift was anchored into. And granted, there was probably a lot of debris impacts here, and we're going to talk about that in the assumptions in a second, but I thought it would be really interesting to see, okay, assuming debris wasn't the primary factor of failure, what wind speed would be needed in order to cause this thing to pull out of the ground? Here we have our assumptions. So for this analysis, we're assuming that there was no significant debris impacts. There likely was, given that there is a dent here in the joist cross member here. However, there isn't a big sign of there being an impact on either of these columns here, and nothing in terms of like a paint transfer or anything like that up above that leads me to believe that there was something super significant that hit this thing in order to pull it out of the ground. Given how uniform it's pulled out of the ground, I think that wind load is a big contributing factor that ultimately caused the pullout failure of this car lift. So with some of these other assumptions here, so we're assuming a uniform wind load once again parallel to the failure direction, so the wind is acting purely parallel onto these surfaces here, pushing it directly over. And lastly, that the fact that it was installed correctly into the concrete. This is a big assumption here because depending on the condition of the concrete and stuff like that, you can get some very wildly different answers. And this thing could be significantly weaker if the concrete wasn't poured properly or this thing wasn't anchored into the concrete properly. There's a lot of things that go into that, as we'll get into in a second. Fortunately, I was able to find a user manual for this car lift and ultimately pull out a bunch of information in terms of geometries and the installation practices for this car lift. So that makes my job a heck of a lot easier in terms of not having to eyeball or guesstimate any of the dimensions here. We know exactly what's going on here and exactly how this thing was affixed into the ground. So as we start adding our geometries and details in terms of the anchoring into the ground here, all of this stuff is extremely important. We can kind of nail home our geometries in terms of all of the widths and lengths in terms of moment arms, as well as all of the bolt engagement and distances needed in order to calculate how the failure occurred out of the concrete, including the material property of the concrete compressive strength of 3000 psi, which in the installation directions here, it said that the concrete base shall have a compression strength of at least 3000 psi and a thickness of 4 inches in order to have the proper installation depth. and proper adherence to the standards in order to have this car lift safely used. So here are some of our forces at play. We're going to have, you know, each of the wind forces on the center of these columns, as well as on the center of the joist here that goes across connecting the two columns. And then we have the reactionary moments that the bolts are resisting against the wind loading. Here we are taking a look at concrete pullout, which is the main failure here ultimately that results in this car lift getting pushed over. Concrete fails in a very interesting fashion. It's not like steel or any of these other traditional, you know, more uniform style metal materials. Concrete is very good in compression, but very bad in tension and shear. And in the case of, you know, these concrete pullouts, we're looking at axial tensile failures of the concrete. And it doesn't fail in a straight line out. What ultimately happens is you get something called a fracture cone. So starting at the base of the anchoring point, you basically get a cone coming out of the fracture location. So as you pull axially on your anchoring bolt, the concrete is going to chip out in this kind of cone fashion outward. Given the way concrete fails, we have special force equations to use in order to determine the concrete pullout failure. Ultimately, because the tensile load is so much weaker than the compressive load, we have to use this reduction factor with the square root of the compressive load failure to get an accurate representation of the strength and tension. Obviously, it is a much weaker number than that of the compressive load. Then we have the concrete effective cone area. So this is the amount of area that that cone is having to deal with that load. Basically, as stresses are distributed through the cone before failure, this is the effective area that the concrete has to work with in order to distribute that load as you're axially pulling on it. And then we solve for that effective area here within the equation. If we take our bolt failure criteria and plug it into our sum of the moments equation, we ultimately have the two moments of the bases. So that's this 2MB term here. And then we have the moments from the two columns, from the wind forces on those two columns, and this center joist. So ultimately, if we look at the equation as a whole, we have the force of the wind on the two columns, so 2 times F times halfway up the column. So that's our moment arm there. Then we have the central joist up here, which is the full height of the car lift, and then that force of drag from that central column. And then we have finally our two moments about the bases of the column, which basically comprises of the 5 bolts on each of the columns, the failure criteria of each of those bolts, and then the distance from the center of each of those columns. So that gives you the moment arms on those ends that ultimately comprise this final bending moment equation. As we dive into it, we can solve, again, like the wind turbine problem, we can solve for everything except for the velocity of the wind for both the column and the joist that goes across here. We have all of those terms available to us, you know, the coefficient of drag, the density of air, the platform area that the wind sees, and we get these two terms just with V unknown. We plug all of this information into our bending moments equation and start to isolate for V. We know all the terms except for V, so once again, we solve everything out, and assuming a purely wind-driven failure on this car lift, it would take a wind speed of 157 miles per hour in order to have concrete failures of those anchor bolts. Like I said earlier, I do believe debris is a contributing factor in the failure here, and I think it's important that we note that this probably wasn't a perfect installation. There's a lot of things that have to go right in order to have a perfect installation into concrete. Granted, there's a lot of safety factors that go into play in order to ensure that even if there are some steps missed or the curing process wasn't perfect, that the lift isn't going to fail catastrophically, given that this is such an important piece of equipment to have very strict safety standards around, given that there are going to be people underneath heavy cars that if that thing collapses, there are going to be people killed. So it's important to note that this thing is over-engineered to a point where it shouldn't fail. But nonetheless, one of the main things that sticks out to me is that there is no concrete really remaining on each of the anchor bolts. That's likely because of the fact that this was installed well after the concrete pad was poured, which is standard practice. You use a drill to drill out the concrete, and then you put in these anchor bolts and then torque them down on top, and they bite into the concrete from the bottom. So I don't think there really should be concrete on those anchor bolts, but I think I would see a little bit more residue of some sort on these anchor bolts if there was, a more permanent adherence to these bolts. And, so something tells me that given the debris factor and the fact that there's no concrete on the bolts, this probably failed in less wind speed than what was calculated. This next thing that we're going to analyze is a personal favorite of mine. This is something that we have seen before with other tornadoes, but this is the first time I've gotten the opportunity to really dive into one on a damage analysis stream. But this one was submitted to me once again on Twitter, and this is a manhole that was sucked out of its hole in the path of the tornado. And this manhole in particular, based on some geolocating, the submitter didn't tell me exactly where it was, but based on these cracks in the seams of the street concrete here, I was able to isolate it to the intersection of East Iowa Street and 7th Street in Greenfield, which was right around the core of that tornado. So some very intense wind speeds. And, obviously there's, a section of roof here and a bunch of other debris kind of around it at the moment. So obviously this was in a very intense part of the tornado, so it's not overly surprising to see, but I think the principles behind how this is able to happen is super fascinating. This is the perfect example to use to get away from, the typical bending moments and stuff that we have been using in the force of drag equations. This is a great illustrator of what is called Bernoulli's principle. Bernoulli's principle states that there is a relationship between a fluid's speed, pressure, as well as its potential energy. And in the case of this manhole cover, if you have a velocity increase on one side, you must have a pressure drop as well. As we dive into it here, this is a 2-foot manhole cover with a 2-inch depth. So ultimately, what we can do with Bernoulli's here is get that final velocity based on the other knowns that we have. So within the sewer itself, there is no wind. It's a velocity of 0. And ultimately, there are two forces at play. Because of the pressure differential of the speed of the wind on top, you're going to ultimately get a lifting force from the wind. And beneath it, you obviously have the weight due to gravity. Here we have a number of terms that we need in order to solve for the weight and the wind force that is acting upon the cover here. So these three terms are important in order to get the weight of the cover. So we have the density of cast iron. These manhole covers are made from cast iron. Very heavy manhole covers. Obviously, they have to stay in the street and they can't come out. So that's why they're really heavy. Then we have the gravitational acceleration constant, g, 32.2 feet per second squared. And then, of course, the volume of the cover, which we can get from just a simple cylindrical volume formula and the geometries that we already have at play. Then, of course, we have the area exposed to the wind, which is simply just the area of a circle. So we have to set our weight equal to the force of the uplift from the wind. We do that via the weight of our manhole cover, which we get ultimately to be 232 pounds force. And then here is our Bernoulli's principle governing equation. So ultimately you have the pressure due to the wind, the velocity impact due to the wind, the gravitational potential energy constant due to the wind. Those are the three terms in Bernoulli's equation. And what we can do here is get rid of a lot of these terms. We don't need them. So ultimately, because roughly this thing is only 2 inches thick, so the height difference isn't really a factor here. It's almost negligible. So because these two heights are the same, these two terms are just going to cancel each other out. Meanwhile, the velocity term underneath the cover, the velocity is 0 under there. So that 0 there is just going to cancel that whole term out. So as we condense this equation down, we ultimately get a pressure differential because of the pressure outside versus underneath in the sewer equal to that velocity term of Bernoulli's. And because we know that pressure differential, we can set that equal to our force due to the wind over the exposed area of the manhole cover, because at the end of the day, pressure is just force over area. And we plug in that weight as well as that area to get 73.8 pounds per square foot. So that is the pressure that needs to happen on that manhole cover in order to achieve that equilibrium. So we ultimately only have one variable left over that we need to solve for, which is that wind velocity. And when we do that, we get 249 feet per second, which comes out to 170 miles per hour. The most important thing to note with this analysis here is that that wind speed is only what is needed to achieve equilibrium. So to get your force of the wind pulling it out equal to the force of the weight pulling it back down into the hole. So once you achieve that equilibrium, this thing is effectively neutrally balanced. You have to go faster than 170 miles per hour in order to create a force imbalance, in order to accelerate the manhole cover out of the hole. The last thing we're going to look at for today's damage analysis is extremely intriguing to me, and I think goes to show just how powerful the wind speeds can be extremely low to the ground when it comes to the impacts of a subvortex or a very tightly wrapped core of a tornado. These are some parking stops in a parking lot that is across the street from an emergency room in Greenfield, Iowa. An important thing to note about this parking lot is that it is extremely new. It was built within the past year based on satellite imagery. The most recent Google Earth satellite imagery up close for Greenfield, Iowa was in August of 2023, and this parking lot did not exist then. So at the time of this tornado, this parking lot was only a couple of months old at the most. As we take a look at these parking stops, they all exhibit a similar failure, whether it be one of the anchor points or both of the anchor points. In the case of this one here, it just didn't fully tear out yet, but it's a similar instance of concrete edge breakout. So similar to the pullout failures that we saw with the car lift, but this is in a shear direction versus a tensile load direction when it comes to concrete. And as we mentioned earlier, concrete really good in compression, but really poor performing when it comes to tensile loads and shear loads. Remember, tensile loads are pulling apart, shear loads are pulling across. Like we said, we can see this edge breakout condition here. We can see it starting to occur here. I mean, essentially it's already failed. They just didn't get moved. And there are a number of other parking barriers here that this one over here fully failed breaking out of both edges. So some extreme forces went into play here. As we can see, there's a little bit of debris built up on this guy here. So we can tell that the wind was definitely occurring this low to the ground. This smooth parking lot surface likely, provided very little friction for the air to work upon. So that boundary layer that provides some sort of cushion from the tornadic velocities above was almost non-existent in this case, based on my estimation and what I'm seeing from the visuals of this damage. Granted, debris impacts could be a case here, but because of the fact that it occurred across all of these parking barriers almost uniformly, makes me believe that it's a uniform wind load. If there was a debris impact, I think the failure of these parking stops would be much more catastrophic, and you would see almost smashed concrete barriers versus just simple tear-outs from their anchorings. You would see the thing smashed in half, smashed at the ends, XYZ, but you wouldn't see perfect tear-outs across all of these parking barriers. So let's get into some of the assumptions. This is going to be assuming a uniform wind load perpendicular to the long axis, so it's going to be directly impacting the face of this parking stop. This is going to be treated as uncracked concrete, given the fact that they were so new and that there was no significant debris impacts based on the imagery provided. Here are our geometries as well as our concrete compressive strength again. And then this is our free body diagram, diagramming out our forces at play. So obviously the big external force here is going to be the force due to the wind, but we also have a static friction force. Given this thing is sitting on the ground, there are a couple of anchors embedded into this thing, but at the same time too, friction is still a factor that we need to consider. Just because it's anchored doesn't mean friction is still not playing a role here. So we have that friction force combating it. We have the weight due to gravity of this thing, which is important to know for the friction force. And then we have the two, what we're calling tear out forces, because we ultimately know that's where the failure is going to be. But those are going to be the opposing forces via those two parking anchors. We're going to be looking at this purely in the X direction, as those are the important dimensions at play in order to analyze this failure. So we have the force due to the wind, the two anchors, as well as the friction force. So the force of the wind is directly combating the two anchors and that friction force. Solving for the friction force, that's pretty simple. You just have your coefficient of static friction as well as the normal force, which in this case happens to be just the weight of this concrete parking stop. The coefficient of static friction for the case of concrete on concrete is 0.8, and like I said, the normal force is just equal to our weight force. So ultimately we were able to get the weight of this concrete barrier from the data sheet, and it ultimately comes out to a friction force of 152 pounds force. Now we get into the tear out force, where things get a little weird. This is a funky equation that I had to dig into some concrete failure texts about. And ultimately this is what happens when you get an edge breakout from a concrete structure. Things in tension and things in compression are a little easier to deal with. Shear tends to be a little bit tricky. Shear is not as proportional as tensile or compressive failures, and in the case of concrete it gets even weirder. So you have to pull out these kind of experimentally derived equations in order to get a reasonable answer, and that's where all of these little correctional factors like this beta and alpha term here come into play based on the geometries. These are experimentally derived, but nonetheless we use some of our concrete barrier geometries here in order to derive those corrective factors. And then ultimately we get each of the tear out forces required. So you get obviously the diameter of the hole of the rebar that this thing's interacting with. You get the depth of the concrete, all those types of terms, as well as your corrective factors, as well as the distance from the closest edge allowing for tear out. And we're going to get each of those tear out forces on either side to be 267.9 pounds force. We're going to plug all of these values in, and that just leaves our force of drag to be, or the force of the wind, left in order to solve for. And obviously the velocity term is going to be the one thing that we don't know. So we have our density of air, we have our coefficient of drag of the long parking stop, and then ultimately as well we have the area of the platform that the wind sees, which ends up being 3 square feet, given that this thing is 6 inches tall and 6 feet long. We plug all of that in, and that just leaves behind our V term. So we solve for V, and we get a final answer of 414 feet per second, or 283 miles per hour. Now that is a very fast wind speed that sounds almost a little too unrealistic if you ask me. But if we go back into our equations again, let's look here. We have our K factor here, which is our uncracked concrete correctional factor. So like I said at the beginning, this is assuming that this is an uncracked concrete condition. Granted, there's another K factor we can use here. Instead, we can change that to a cracked concrete correction factor of 1.7, so slightly less, making the concrete even weaker than it already is. So if we plug that in, our tear out force comes down to 188.7 pounds force. We redo our equations again in the sum of forces in the X direction, as well as solving for V here, and we get 363 feet per second, or 247 miles per hour. So nonetheless, cracked concrete or uncracked concrete, This is an extremely fast wind speed. Now, there are a number of things to consider here. There could be potential debris impacts that are further weakening it. There are inconsistencies in the concrete, allowing it to be weaker in general. But nonetheless, the fact that these tear-outs occurred universally across all of these parking barriers is extremely interesting to me, and it leads me to believe that there were wind speeds across all of these barriers here that were capable of doing this. If it was an isolated case, if it was just one parking barrier, then I could chalk it up to something like a debris impact. But in this case here, we can see 5 in a row parking barriers that all exhibited a concrete tear-out failure. This is kind of a smoking gun for me. And if we zoom out real quick, things get even weirder, and it's hard to wrap your head around because tornadic debris damage analysis is so chaotic and it breaks conventional thinking sometimes. And that's what makes what forensics tornado engineering so difficult, is that there are so many factors to contribute to, and some of the things that we see are just so beyond what we have current understanding of that it almost breaks our mind. Let's zoom out real quick with some drone footage. Thanks to Chris Riske of High Risk Chris, he had some drone footage from right after the tornado and captured the parking lot in question in the footage. The main thing that I noticed is the gradient of the damage is extremely sharp, which leads me to believe that this was some serious vorticity stretching occurring at the end of this tornado's life, dramatically reducing the width of the tornado and increasing the velocity thanks to the conservation of angular momentum that we talked about earlier. But let's note some of the vehicles remaining in the parking lot. If there are 200 plus mile per hour winds here, you would think that these vehicles would be lofted. But if we look just west of the parking lot, we see that we have an exploded house, this one over here earning an EF4 damage indicator thanks to its great construction. But nonetheless, the vehicles that were impacted were isolated to this half of the parking lot here. Whereas if we look upstream a little bit, there are some randomly placed cars kind of in the backyards of the houses of the street to the north of this parking lot. While we cannot confirm that these cars came from the parking lot, I do think it's unusual that these vehicles are back over here if they had come from the street to the north here. Now, the next thing you can point to are the rocks that are behind these concrete parking stops. And while most people might argue that those would be, long gone if those types of wind speeds were exposed to this area, I think in this case, what happens is there is an extreme drag wake behind those parking stops that is shielding those rocks from those tornadic wind speeds. And if we look where there were failures, you can see rocks that have been blown further upstream. With wind speeds that fast, I think the drag wakes are going to extend multiple feet behind, and it is really shielding those rocks from being subjected to wind loads at that low of a level. I think given the extremely sharp gradient that we're seeing with that hospital across the street there virtually being untouched and cars in the parking lot, you can almost draw a perfect line to where there was extreme damage versus almost EF0, EF1 type damage. I think this could have been the result of a really strong inflow jet or something along those lines associated with a suction vortex blasting that northwest corner of the parking lot with such extreme winds at such fast rate that it simply just eroded away those parking blocks and took the cars that were there with it. Whether, like I said, we can't prove that those cars came from the parking lot, but just based on what we're seeing here, that would make sense in my eyes. It's a stretch to conclude that, but at the same time too, I think given the fact that we saw multiple of these concrete parking stops failed in this fashion, leads me to believe that universal wind loads were applied to all of them, and we can't simply just chalk it up to debris impacts. With all of that said, this brings in the conclusion to this damage analysis of the Greenfield, Iowa EF4 Tornado. I think it goes without question to say that this was an extremely violent tornado and ultimately might have been the strongest of 2024, at least thus far, assuming nothing happens in the next couple months. Given some of the non-traditional DIs involved here, as well as the findings from the Doppler on Wheels program, I think this is without question a tornado capable of EF5 damage. But of course, as mentioned before, the limitations of the EF scale are going to prevent it from earning an EF5 rating at the end of the day. I think if there is a modified EF scale or something along those lines, I think Greenfield would ultimately fall into an EF5 category in my estimation. I think maybe one of the biggest takeaways here is the craziness of vorticity stretching. Remember that this tornado at its peak width was almost a mile wide, and by the time it reached Greenfield, it was only a couple of blocks wide. So that angular momentum really just ramped up the intensity of this tornado at the worst possible timing when it comes to the residents of Greenfield. That is it for this installment of the damage analysis series here on the June 1st channel. Thank you so much for watching, and please keep the residents of Greenfield in mind when we look back at this damage. It is incredibly powerful and fascinating stuff, but at the end of the day, this is a very real-life impact for these people, and for many of them, it's the worst day of their lives. So that's something that we must take consideration in. With all of that said, thank you so much for watching, and please stay safe out there when it comes to severe weather.